Okay, so welcome everyone to today's IAMP One World Mathematical Physics seminar. It's a great pleasure to introduce today's speaker, Serena Cenatiempo from GSSI L'Aquila. And Serena will tell us about trial states for the zero temperature dilute Bose gas. And as usual, the seminar will be recorded and you will be able then to watch it online on YouTube. And Serena, we're looking forward to your talk.
Thanks a lot, Marcello. And before starting, let me warmly thank the organizer of this One World Mathematical Physics seminar, which provides us such a broad overview of the recent research, current research in mathematical physics. We are very grateful to you, Hal, Jan, Kasia, and Marcello. Thanks a lot for your job. And in this talk, I'm going to present a few results obtained in collaboration with Giulia Basti, Chiara Boccato, Christian Brennecke, Cristina Caraci, Alessandro Olgiati, Giulio Pasqualetti, and Benjamin Schlein concerning the zero temperature dilute Bose gas. But actually, hopefully, so my aim would also be to give, even though a partial, but some overview, more generally of the understanding that the mathematical community has reached in the past 50 years about this topic, at least partially, because much more results are available than the one I'm going to present, and many experts are here in the talk that I really invite to intervene. And my talk is something is missing because most of the things I will be telling I also learned from you when I start working on these topics. The main character of our talk would be a system of M bosons on a torus of side length L, just to take the situation as simpler as possible, then extension to more general situation, trapping potential as possible, but just to communicate the main idea, we prefer settings. For the full talk, we will stay in the simpler case. So our capital N boson will be interacting with a spherically symmetric two-body potential that will be not negative, and again, for simplicity, we assume it to be a compact support, and R will be the support of the potential. So this is our Hamiltonian and body Hamiltonian, which is acting on the space of n particle wave function, and here S stands for symmetric under the exchange of particles because we are dealing with bosons. A striking phenomena that we observe in this system is the occurrence of Bose-Einstein condensation, which is pretty clear if we look to the free case. Namely, here the ground state wave function is just the constant wave function on the box. So each particle just occupied the zero momentum state. So the wave function in the box corresponding to P equal to 0. Now we expect this critical phenomenon, so the fact that the macroscopic fraction of particles occupy a single quantum state, also to survive in presence of interaction, maybe a sufficiently weak interaction. And so the mathematical challenge here is to provide the rigorous proof of this fact, and possibly also allowing to understand which are the regime of parameters for which condensation also occurs for interacting system. So when particles are interacting, of course, it does make no sense to speak about one particle occupation, but we can give a sense to that by introducing the reduced one particle density matrix, which is just an operator which is obtained taking the projection onto the many particle wave function and then integrating all the degree of freedom beside one, no matter which one, because the wave function is symmetric. Then the one particle, the Silhouette's density matrix, which is a sort of quantum marginal in a sense, contains all the information concerning one particle observables. And then the natural definition is that we say that the Bose-Einstein condensation in the state psi n occurs if the corresponding one particle density matrix has a eigenvalue of order 1 in the thermodynamic limit when we send a number of particles in the sides of the box to infinity by keeping the density of the system fixed. Namely, what we are saying is that our many particle system can be effectively seen as a superposition of one particle states, and with probability close to 1, the system will be found in the one particle state which corresponds to the eigenvector phi naught, which is the condensate wave function. Okay, unfortunately, or even surprising, a proof of Bose-Einstein condensation in the thermodynamic limit is still beyond of the reach of current methods. Only the known results so far concern only for a very specific model, hardcore boson half filling, where reflection positivity is used, so a very specific situation. Or we have at our disposal perturbative results that date back to work of Benfatto, and a very challenging Lee-Huang project devoted really to this big challenge. But still in the mathematical community, it has been pursued in a complementary approach. Namely, why don't we try to investigate other aspects of the macroscopic behavior of low temperature gas, for example, the thermodynamic functions, which because also possibly we can get some more understanding on the behavior of the Bose-Einstein of dilute Bose gas that may be also useful in the future, also to go back to this much more challenging, of course, interesting result. So in this talk, we will in fact focus on one macroscopic observable, which is the ground state energy, or one thermodynamic function, which is the ground state energy. So the relevant observable at 0 temperature. Here in the physics literature, exists a very clear or a very precise asymptotic for the ground state energy of the system, or better, the specific ground state energy, the energy divided by the volume of the system in the thermodynamic limit, in the situation where the system is dilute. Dilute means that the scattering length, the density of the system times the cube of the scattering length of the interaction, which is a parameter associated to the body potential that I will describe in a moment, representing the effective range of the interaction, basically. Well, when this parameter is small enough, we expect this to be the asymptotic for the ground state energy. And in fact, to make a long story short, in the past years, we have in fact, we have reached almost a final proof for this formula. In fact, this has established it as a lower bound for any potential, including the hardcore interaction, and as an upper bound up to a bit more than L1 potential, let's say, in these papers. But these dots here are in fact part of this talk, because these are all the story, say, the ideas that has led the community to an understanding of this formula up to this famous second order correction, which is known as the Lee-Huang-Yang correction. And in fact, this story would just try to tell this story, just focusing on the upper bounds, just also for sake of time. So just telling which are the trial state which has been presented in the mathematical, which have been developed in the mathematical physics community in order to understand this problem, this formula. So the question we'll be asking ourselves during this talk is, which are the relevant correlation when we want to match this expansion at the desired order? So which one at the leading order, which one for going at second order, and so on. And which are these relevant correlation? Really, we can answer this question just by providing trial state for capturing the energy at the order we wish. So the very first trial state we will map is the Jastrow function, or Dyson-Jastrow function, or I think also other names are attached to this trial state. So the basic idea in this trial state is, well, since the system is really dilute, the only relevant correlation that we should take into account are those due to two-body scattering events. Two-body scattering events are described by the solution of this equation, the scattering equation, with the condition f going to 1 when the distance goes to infinity. So for large x, the solution of this equation in 3 dimensions behaves as 1 minus a over x, and a, this constant here, is what is called the scattering length of B. In the case of the hard sphere, potentially it coincides with the radius of the hard sphere. So in a sense, the scattering length is just an effective range of our interaction in more general case. So now the idea is pick some L, which is much smaller than the size length of the box and much larger than the scattering length. And take now FL to be just a modification of this function, just because it should be just cut off on a distance L. So maybe just take the same F, but with the boundary condition 1 on a ball L. Well, then you expect a good trial state for your many particle system, just be given that the product of all the possible two-body scattering events among the particles. And this, in fact, can be made rigorous. It was already as an upper bound available in the work of Dyson for the hardcore case, and then extending to more general potential, and also with a corresponding matching lower by Lee-Huang-Yang in 1998, they showed that in fact, if we refer for the upper bound, which is the goal of our talk, in fact, trial state of this form allows to capture the leading order term. And I would like to briefly sketch the computation for the energy of this wave function in the case of the hardcore potential, because it's the simplest, just to understand the powerful of this trial state, and also maybe its difficulty or its limitations. Okay, so just consider now the hardcore problems. We have capital N hardcore spheres of radius n. And now let me define the ground state solution with which I want to build my Jastrow function in this way, a bit differently as before. We will see why it's useful. Just as the solution of a Neumann problem minus Laplacian, the ground state solution of this Neumann problem minus Laplacian equal lambda f inside in the distances between the scattering length and L. And then we extend just to 0. So if this is just our distance, here we have A, here we have L, and here is the size of the box. So we are taking the solution of minus Laplacian lambda up to here, and then extending to 1 and to 0 inside. And this will be our scattering solution, the one that we'll be using to describe two-body correlation. Now let's build the Jastrow function, and let's try to compute the kinetic energy in the variable xa of this function, divided by the norm. Well, you see that we have two possibilities, either the two gradients fall on the same variable, or on different variables. Then you have here two body terms, but believe me, this can be just bounded, we've seen in a moment. But then here, when the Laplacian appears, then it's useful we can use a scattering equation, and we see that the kinetic energy of the Jastrow function produce this quantity lambda L if L times a chi characteristic function on the ball L. So if now we use the permutation symmetry and just ask ourselves, which is then the expectation of the kinetic energy on the psi, notice that psi, of course, is a well-defined wave function in the hardcore domain because it vanishes as long as whatever two particles comes too close than A, just for the definition of our scattering function. Well, now we compute the kinetic energy of the Jastrow function, and we get from this term here just n squared, the eigenvalue lambda L, the chi, and then the product over all the half here and then and the denominator. And this error comes from a bound that you can get on these three body terms, let's say. Now in the denominator, you now want to use a cancellation between the numerator and the denominator. So in the denominator, you can use that if you take the function that counts how far you are from 1 using FL, then the norm is small with this small L, and this allows you to get a lower bound on the denominator, which here can be made small if L is much smaller than R to the minus, rho to the minus 1/2. So just putting all together, I'm very quick, but it's just to give an idea. So just putting all together, you can conclude that in fact you get just from the bound on this eigenvalue that goes as 1 over L cubed, then precisely compensate with the integral over KL at the numerator. So it, and then gives you 4 pi A naught rho. And then you have two sorts of errors. One kind of error, which is just coming from the expansion of this eigenvalue. And this error would like L to be large in a sense. And then another error, which is coming both from the three-body term and the denominator bound. And this needs L to be small. And then you just obtain the wished result by taking the optimal choice for L, which is rho to the minus 1/3. So if you use a Jastrow function where you put this short range correlation, short meaning L much more of the order rho minus 1/3, then you are able to capture the leading order term. But of course, you would love to go further, right? You would like just to understand the next order correction. And this seems complex to be achieved with the Jastrow function itself, because, well, we would need to put correlation on a longer scale, but then on a longer scale, we cannot use these tricks to bounce this integral. We should really manage to take into account cancellation from numerator and denominator in a more clever way. So in fact, the path that the mathematical community followed to go to the second order is a bit complementary and goes and starts from another heuristic models that was introduced by Bogoliubov that I'm going now to resume. So now our aim is just to build a trial state able to capture the next order subleading correction to the ground-state energy. And we don't want to use the Jastrow function. We want to see another possible trial state. Okay, to explain you, which is like the approach that we will be following, which is in fact due to Bogoliubov, we need to change our description and to pass to the grand canonical approach. So from now on, we will just, the state in our system will be a state where the number of particles is not fixed. It's a Fock space built on this L2 symmetric space with the number of particles n. So our generic vector in the Fock space would be just a collection of vectors with the fixed number of particles, and the zero particle case is just a complex number. Okay, fair enough. Now, since this wave function here, plane wave provide an orthonormal base in our L2 of the torus, it seems natural or it's convenient to introduce some operators that allows us to add the particle with momentum p. So these are called creation operators. So they action exactly the following: take an n-1 particles, just add the n particle in the wave function in the plane wave with momentum p, and then symmetrize over all the particles to create a truly bosonic wave function. Now, for any state with a fixed number of particles in this state, okay, so we are in the simplified state of torus, so we can really look in the Fourier space to what happened. So for any state, you can recognize a string of momenta so that your state is just obtained, creating the particles with momenta p1, p2, pn onto the vacuum state. So these operators are just a convenient way to label our state. Of course, all our state will be of this form or superposition, combination of states of this form. Well, then, in the sense of quadratic forms, then we can write also our Hamiltonian in terms of this operator. Namely, we can really interpret the kinetic energy and the potential energy in terms of creation or annihilation of a particle. For the kinetic energy, in simple, we annihilate a particle with momentum p, we create a particle with momentum p. This basically means that we are counting the number of particles with momentum p, and each of that as a p square contributes with a p square kinetic energy. And sorry, I didn't tell you who A is. A is the adjoint of A star, and one can check that this A and star operator satisfies some canonical commutational relation. And for the interaction, to explain how the interaction looks like, let me use this pictorial representation when I'm just describing the annihilation of these two particles as some incoming errors. Then the particles interact through this potential, and then new particles arise with new labels. So this is really the pictorial representation of an interaction. We want just to express the fact that due to the interaction, the initial momenta of the particle are changed in new momenta, and this is a way to represent this fact, to write this action, in fact, of the operators in the Fock space. Now, the idea of Bogoliubov is the following. Note that now the operator Ester not A naught counts the number of particles with zero momenta, so the number of particles in the condensate. Now, the idea is if the interaction is sufficiently small, we might expect still that this number of particles in the condensate is macroscopically large, where n here means so it's close to n, capital N, and n here is the expected number of the particle on the state we are interested in. Then we have some operators, these A star naught, A naught, that basically are huge, square root of n. So in fact, while their commutation is 1, so in effect they behave as classical objects. So let's just substitute them. So let's just substitute the operator acting on the vacuum by square root of n. So if we do it, this was our pictorial representation. We can just choose to substitute all the 4 by 0, and we have a certain term, which is just a constant term. We can decide to just substitute these 2. Then we have still annihilation and creation operator, and we get a diagonal term in this creation annihilation operator, which also contains the kinetic part besides the contribution of the potential. And then here, if we erase here and open the similar diagram, we get the offered diagonal term. And this row comes from the fact that every time we add a line 0, we are also adding a square root of n, and then we add 1 over lambda in front of the potential of the interaction. So this row is really coming from n over lambda. Okay, so now here we have several terms, and then there will be more terms involving more than 3 particles outside the condensate. But now just assume that Weekend terms, you can prove that they are negligible. If you were allowed to say that, then you know how to build a good trial state for the Hamiltonian up to here, right? It's just sufficient to take the operator that diagonalizes this quadratic part. And this is a well-known operator. It's an operator which has this form. So it's still an operator which is off diagonal in this creation annihilation operator. It has a kernel tau, and the kernel tau is really related to the coefficient here, Fp, and let's call it Gp of the diagonal and not diagonal part. So this is Gp minus Gp over Fp. So once you have the quadratic Hamiltonian, you know how to build the operator that diagonalize it. And it's also an operator whose action is explicit in the Fock space. It's just the cosh A, so the action on A is just cosh A star plus sinh A. And also the condensate component, that one that Bogoliubov have just obtained with the replacement, well, it can be implemented in our trial state by using an operator, which is the Weyl operator, whose action is just a shift of this kind. So where you have p equals 0, you also had this square root contribution that comes from the condensate. We are very close to the solution. So it seems that we have a good candidate for a trial state that would be this guy here. So just acting, oh, sorry. Of course, I forgot something, right? We should put also the condensate here. So just you put, so your trial state would be create the condensate, put this correlation that diagonalize, and then evaluate on the vacuum. And this is the trial state. But the point is that, well, this tau p is not really enough because it doesn't allow you to reconstruct the scattering length of the potential. In fact, you may notice that this Lee-Huang-Yang formula has a striking property that is, it only depends to the interaction through the scattering length of the interaction and not on details of the potential. While here, this tau, it's really the potential depending. But in fact, it has been showed that states of this form, exactly as we have seen before, so condensate given by a Weil operator, Bogoliubov transformation with a certain Kelvin, plus the vacuum state, really allow to recover the Lee-Huang-Yang correction in the limit of weak potentials. Okay, so if you are good, if you are fine with weak potential, these are in fact good trial states, but I should really stress that then nu should be chosen differently according to which momenta you are considering. In a sense, P should be related to the scattering equation or the scattering function for large momenta, high momenta, where high means much higher than what is called the healing length, or let's say high means on the order of the range, inverse range of the potential. Let's put it like that. And then on low momenta, you should use some renormalized version of this tau. So some sort of this current here, but where here does not appears the potential, but appears the potential convoluted with the scattering function. So something that in zero, it's close to the scattering length. But I didn't want to enter in the detail of the trial state that were very nicely illustrated in this paper by Erdo, Schlein, Yao. And also in the paper by Napurkowski, Royer, Soilwaits was explicitly shown that state of this form that are known as quasi-free state cannot capture the Lee-Huang-Yang correction. So the Lee-Huang-Yang correction can only be captured, so the order, but not the precise constant, I mean. But the message I wanted to say, okay, now there is a natural class of trial state inspired by Bogoliubov theory that are built by action of simpler unitary operator in the Fock space. So in fact, as I was telling, the trial state built with this Bogoliubov intuition were the one that allowed to pursue this paper. So this one is still okay. So here you have a quasi-free state of the type that we have discussed. For getting the true Lee-Huang-Yang term with the correct order for also large potential, you need to add another operator, which takes into account for excitation, for correlation among triples of excitation. And I will comment on it in a moment. So I wanted now, so okay, so this Bogoliubov inspired trial state has allowed us to reach, in fact, as an upper bound, the goal of proving the Lee-Huang-Yang formula. They are very nice because they use explicit Fock space unitary transformation, but they have a very bad limitation, which is they are not suited for the hardcore case. Basically, in this trial case, you are just taking a few correlations, the more relevant to get the Lee-Huang-Yang correction, but you are not putting correlation among all the particles as it was in the Jastrow function. So in fact, you are building that if you just use this this kind of trial state, you cannot stay in the hardcore case domain, because you are not guaranteed that any time the particles are too close, then the wave function becomes zero. And that's indeed the problem that you encounter in the Gross-Pitaevskii case, and that in the hard sphere case, and that make the upper bound still open in the thermodynamic limit for the hardcore case. But still something we can say also in the hardcore case, if it's not for the thermodynamic limit, then it's for another regime, which still has some interest, which is physical interest and also relation, a strict relation with the thermodynamic limit, as I will show, I hope, towards the very end, which is the Gross-Pitaevskii regime. So in this Gross-Pitaevskii regime, now your capital N bosons live on a unit torus. And your potential scales with the number of particles, and in particular, the range of the potential is order 1 over m, and the intensity of the potential grows as m squared. So the trait of this effective description is the following. You have that the range of interaction is much smaller than the typical distance among the particles. n to the minus 3. But then the range of the interaction is on the same order of the scattering length. So this makes the problem sharing some of the difficulties that also are common, are seen in the more complicated thermodynamic limit. Typical interaction in the Gross-Pitaevskii regime are very strong interactions that, however, happen very rarely. In fact, if you have a fixed target particle, then the probability of interaction with one of the other particles is order n to the minus 2. Then at the end, the contribution to the energy coming from all the n-square interaction is order n. So despite the fact that you have such intense interaction being so improbable to be interacting, then the overall contribution is order n. So we are just describing very strong but rare interaction. In fact, this model that has been introduced by Lee-Huang-Yang first in 2000 provides an amazing description for the experiment of Bose-Einstein condensation in cold trapped gas. So for this Gross-Pitaevskii regime, in fact, we know a lot. Is it possible really to provide not only information on the ground state energy of the system, which has this form that if with the Lee-Huang-Yang formula, namely if we here could substitute the sum with an integral, we would get the Lee-Huang-Yang correction. Then of course, this is not what we can do here because P being on the sides box of order 1 is just like that, so it's fixed. But anyway, so not only we have like an information on the ground state energy of the system, but for this Gross-Pitaevskii regime, you also are allowed, we also can show that low energy state exhibit Bose-Einstein condensation. But okay, this is just because we are not speaking about Bose-Einstein condensation in thermodynamic limit, it's just a local condensation that we are proving here, condensation on a finite size box. And more remarkably, we can give, we also have information on the spectrum of the system. And we know a lot in sense that recent results also allowed to extend all this second order picture. Here, I mean for second order that you really capture the analogous of the Lee-Huang-Yang correction and the spectrum of low energy excitation up to errors going to 0 with n. Well, this second order picture can also be obtained in the more general case of a trapping potential, as is done in this paper. Note still that we need some regularity on V. It can be a bit reduced, but for sure the methods at the core of this proof are not good for the hardcore case. But still we are speaking about trial state. Let me at least show you which is the trial state that gives as an upper bound this ground state energy. It's again a Bogoliubov-like trial state, but also in this Gross-Pitaevskii regime, as in the thermodynamic limit, if you want to obtain the second order correction, you need to add more than the Bogoliubov correlation, more than correlation expressed by couples of excitation. And in fact, the good trial state has this form. So now I'm just here for this Gross-Pitaevskii case. We cannot go to the grand canonical picture because all the grand canonical and canonical ensembles are equivalent in the thermodynamic limit, but here we are just on a fixed box. So we need to work on the L2 space. So I cannot use while operator. I use some analogous on them that factorize the condensate but stays on the, allowed me to stay on the fixed number of particle state, but I'm not going to define them. Just think to that UN as an analogous of the while operator. It's just a map factorizing out the condensate. So we factorize the condensate. We add some Bogoliubov-like transformation. Again, here with new operator, just because you want to stay with the space with fixed number of particles. So this B operator are operators that create an annihilate excitation, but out of the condensate. So the action is just like erasing a particle in the condensate, creating, for example, an excitation, and then divided by the number of particles in the condensate. So besides the fact that you should be careful to stay in the fixed number of particle states, then the trial state is really the one we have seen before, condensate, pair of excitation, but there is an additional unitary operator. This additional unitary operator, well, it is cubic in these operators creating particles outside the condensate. And so you might think that then it's really just desperate to compute the exponential of this operator, but you can do it because here there is 1 over square root of n in front that helps your life. And because you recognize that you can introduce useful cutoff in the moment of these particles. So in particular, the kind of scattering that you are describing, while here you are describing just zero momentum particles, 2 particles in the condensate, giving rise to 2 particles with high momentum, let's say. So here the kind of scattering that you are describing is just you have 1 particle in the condensate, 1 particle with some low momenta, so still close to the condensate, which gives rise to 2 excited particles. So, and these low and high momenta are also physical behavior. So these are related, in fact, to the inverse healing length of our condensate, which is just proportional to the square root of the scattering length in the Gross-Pitaevskii case. So here we have this low momenta and the high momenta, which is just high, let's say, close to the inverse range of the potential. Remember that for the Gross-Pitaevskii case, R is n to the minus 1. Okay, also this new here, as before, is just like related to the scattering length for high momenta and related to a renormalized version of Bogoliubov diagonalizing kernel for low momenta. Again, it might seem a complicated trial state, but the idea that does encode is basically, again, you have unitary operators that describe scattering of particles from the condensate to outside the condensate, which has a precise form, some kernels, which are really related to the physics of the system in a sense. So the fact that high energy or correlation, let's say low in space, like this short scale correlation that we were also seeing in the Jastrow case, these are described by solution of the scattering equation. And then correlation on longer scales are described by something which is related to effective quadratic Hamiltonian. A bit in the spirit, the last one, of what you would find in a renormalization group approach, in which at the end, after several steps in your renormalization, the effect of your quartic and cubic interaction are just giving you a renormalized quadratic interaction that then you may renormalize, you may diagonalize. So what is left open is really now the hardcore gas. And in the hardcore gas, let's go back to our main player, the Jastrow function. It was so well suited for dealing for hardcore gas, right? Because as I told you, if we now take this FL, which is just 0 within the range of the hardcore, and then it becomes 1 outside a radius L, and then it's basically 1 over x between. Well, this one, then if I take product of this L, then I have a wave function that it's perfectly in the hardcore domain. And also we saw that for small L, the computation of the energy of this function was easy to obtain for small L, because we just the contribution of this Laplacian of psi was coming out as an effective potential in a sense. This lambda L, remember that it was just related to scattering length over L cube. So this lambda L key L, which is a filling here, is 1 over L cube chi x over L. It's a sort of potential that is just appearing from the contribution of the kinetic energy contribution of the Jastrow. But we commented that with the way we know how to deal to that, here we can only treat small L. So a natural question would be how to perturb this structure. Sorry, how can we perturb this Jastrow function to obtain an upper bound capturing the second order term. So we want to keep this nice structure of the Jastrow that guarantees us to stay in the domain, the correct domain, but we want to add something here and still be able to do computation and to recognize the strong cancellation that should be present between the numerator and the denominator. So in fact, our recent work was exactly devoted to this question and to this challenge. And at least for the Gross-Pitaevskii regime, we have now an answer, namely an upper bound capturing the second order Lee-Huang-Yang subleading correction, but for the Gross-Pitaevskii regime. So in the Gross-Pitaevskii regime, our hard sphere was gas as radius A over n, clearly 1 over n, exactly as the range of the interaction in the smooth potential case. So we have this sphere, radius A over n, that moves on the unit torus. And we want to take the infimum of this expectation over all the C that satisfy the hardcore condition that the wave function becomes 0 anytime two particles comes close enough. And in fact, we were able to provide the same upper bound, which holds for the smooth potential as was clearly expected, because it's clear that what we have in mind when we write this formula is that really the only thing that depends in this expression, the only thing that appears in this expression is the scattering length of the interaction, and also scattering length can be associated to the hardcore case. It's in fact the radius of that core. And then we were expecting, of course, to obtain the same formula also for the ground state energy. We were expecting to obtain for the hardcore case the same formula than for the Gross-Pitaevskii case. And indeed, the proof of the trial state that allows you to capture this energy up to smaller error, smaller with them, is exactly what we expect it to be. So just as a Jastrow function multiplied for an n-particle wave function that captures the correlation that are not encoded here. What I mean here is that as we see, we can deal with this Jastrow function that L is very small. In fact, to us, L which be, again, it will be between the scattering length n to the -1, and then it will be much, much smaller than interparticle density. The mean interparticle density in the system. So we want to put with the Jastrow very short range correlation. So basically, here we want to encode only the fact that the particle cannot come too closer than n over m. But then we need another wave function that allows us to put all the correlation, the long scale correlation that we have seen appearing in the Bogoliubov-like trial state. And now the main difficulty is that you have already seen in the other trial state that are shown that this high and low energy correlation are really mixed among themselves. So you cannot really expect to divide the two words of low energy, higher energy correlation. They come together to contribute to the energy. And that's in fact the true challenging when you try to compute the energy of this wave function. And let's see if I'm able in a few minutes to give you the core ideas of that. So just making the computation very similar to the one that I did before. And of course, here there is a Laplacian missing, sorry. So we are just computing the kinetic energy of this new trial function that is now just Jastrow multiplied for 5. Well, if you do like that, with a similar computation, you see that up to a 3-body terms, that let's say that then you can show that this is just controllable, not boundable, just give a small error. You have basically some effective equations, some effective Hamiltonian for your phi appearing. Phi is the short, let's call it just the long range correlation many function, let's say. And then factorize here and here the Jastrow. So suppose you could neglect this term. Suppose this Jastrow term could be neglected. So of course, this will not be say that the Jastrow gave no contribution, right? Because this lambda L, PL, really came out from the kinetic energy of the Jastrow. So in a sense, one can think, okay, I already have the contribution from the Jastrow here, so I can expect that these two are negligible. Then if you could do it, then you would get just that an upper bound for your hardcore Hamiltonian would be just given in terms of an upper bound, but just for the function phi n, so for the function without the Jastrow, on an effective potential of this form here. So kinetic energy plus a potential energy. Well, but this potential energy is something we know how to treat. It's just a scaling potential, even that, as it was the Gross-Pitaevskii scaling, sorry. Just now with this parameter beta, which is less than 1. These are in fact scaling limits that were studied in the literature, interpolating between the mean field regime. Mean field is just 1 over n dx, so very weak collision, but all particles interacting, and the Gross-Pitaevskii case. And this beta potential interpolates among them. And we know how to solve it because it was known from the literature how to treat this kind of potential, how to minimize this effect in Hamiltonian. So now we are very happy. We say, okay, this we can neglect it, then we have an expression for phi. And this expression for phi will be just given as a Bogoliubov trial state, where you have a vacuum, a quasi-free state, and the condensate. We don't need even cubic correlation here because for beta less than 1, for this intermediate potential, in fact, it was proven here that you don't need cubic correlation to get to the Lee-Huang-Yang order. And this new tilde, we know how to build it. It's just related for high energy to the solution of a scattering equation, where here, the potential appearing here is a potential which is just coming from the Jastrow, in a sense. It's just the eigenvalue of the scattering equation minus lambda FL, lambda L FL, times the characteristic function on the ball L. So in fact, you can try to follow this way, and you very easily realize that it's wrong. In fact, the Jastrow factors are not negligible. If you just try to compute the energy of this guy here times the Jastrow function, you will find still a dependence in L, in this small L. That is just something that we introduce fictitiously and should not appear in the expression of the energy. Also, sorry, L is n to the minus beta. So having a term in the energy that are still depending on L is not a good deal, because you will have terms growing with the n. Okay, so this is not the way. In fact, Jastrow factors are not negligible. And what one can show is that still there is an effective Hamiltonian arising from this description here, but it's not obtained by throwing out all the F. In fact, you should keep some F both in the kinetic part, in front of the kinetic part, and in the potential energy. And now still, you know, or you might understand how to to approach the ground state energy of this HF. You will need again a Bogoliubov-like trial state with the quadratic correlation. But now the kernel of the quadratic correlation will be related to a new scattering function here that, as you see, it contains F inside. And remarkably, when you study, so it has this modified kinetic energy and this potential that is not only, so the new effective potential is not only lambda L KL, as it seemed before, but also has FL squared. And in fact, if you now study the solution of the scattering equation, you discover that it's nicely related to the scattering solution. So it's just given from the scattering solution, sorry, this is the scattering solution for the hardcore case. So namely, it's just given from the ratio from the scattering solution for the hardcore on L, so this F and L, and the scattering solution on a much larger, sorry, the picture is awful, but I hope it's clear. It's just the scattering equation for the hardcore case on a much larger scale. And the ratio of the two really defines this function that we need to put in our Bogoliubov transformation to match the correct energy. And maybe it's a bit clear if we look which is the behavior of this 1 over x here. So this f, as we were telling, so this f is just 1 over x inside between the scattering length and f. This is just the hardcore wave function, sorry, the hardcore scattering function. This h is now instead regularized on some distance L. So it just behaves as 1 over nx, but then is regularized on very short scales. So the main difficulty in all this story is that you should really be able to identify cancellation between the numerator and the denominator. So also once that you have identified this effective equation, is not that you have concluded the story. Then there will be several large terms arising both in the numerator and the denominator, and you should like to find a clever way to show that in fact these terms cancel. And this is in fact what can be shown. Just to conclude in the last 5 minutes, let me now tell why this result in the Gross-Pitaevskii case might be useful or promising for the thermodynamic limit, and why it's not so far. So which are the obstructions so far? So it's a well-known fact, again, in the community, that informations that you have on finite size box can be used to get thermodynamic function on thermodynamic box. And I explain better what I mean here. So suppose that you define some scaling limits that now are interpolating from the Gross-Pitaevskii case n square b n x, and the thermodynamic limit that in this rewriting, so in the situation where the box is of order 1, would be just n 2/3 b n 1/3 x. This is just a strange way to write the thermodynamic limit. But why it's clear that it's the thermodynamic limit maybe it is from the following picture. So let's take this Hamiltonian here. So a box of size 1 and scattering length small with m, and just rescale the length. Rescale the length so that the size of the interaction, the range of interaction is of order 1. Then if you do like that, then you will have a box with size growing with n, and then your density depends on n. And then you see immediately that for kappa equal to 2/3, you have rho equal to constant, which is in fact the thermodynamic limit. So really this is a way to write some Hamiltonians that interpolating between GP and thermodynamic limit. Okay, these Hamiltonians are also interesting to study on themselves. There are, in fact, it's possible to prove, for example, Bose-Einstein condensation for some of these kappa, and to have information on the low energy spectrum. This would be completely other story. But for our discussion, what is interesting is that now if you study this small box Hamiltonian, so that here I rewrite it in the form where the potential is just as radius 1, and then the box is increasing with L. So for kappa lower than 2/3, your box is always smaller than the thermodynamics box. This is the L, the size length of the thermodynamic box. But now there are standard technique known as localization technique, allowing you to get lower and upper bound for the ground state energy in the large box, in the thermodynamic box, knowing the energy on this small box. And in fact, one needs kappa to be larger than 0. So you need just to be a bit above Gross-Pitaevskii in order to get the lower bound. That in fact was achieved in these papers, and I recommend to look back to the talk by Søren that was given to the YAP on this topic. And for an upper bound, you need kappa larger than 1/2. So you need to be on a larger box to be able to get the proper information on the thermodynamic limit. And this kappa larger than 5, this comes from the fact that in order to build a trial state, an upper bound trial state from a smaller state, what you want is just like to change your condensate, which is just on the box, the constant function. Then on a larger box, you want to put the to make the condensate 0. Sorry, so just to have an idea. Then the error, and then so that you then can collect many boxes, then you put the box at a distance which is separated by the range of the interaction, and then you get your trial set. But then in passing from the condensate to the condensate with periodic boundary condition to the condensate which is 0 on the boundary and the box, you lose some energy, and this is the energy needed for the fact that you need your box to be sufficiently large. So here the message is, to compute thermodynamic function is sufficient to occur to show the occurrence of Bose-Einstein condensation on local state scales. And in fact, these upper bounds, Yao Yin and the one with Julian Benjamin, were obtained on building on some trial state on this larger scale. And in fact, in our case, this trial state was really inspired from the one that we had, the Gross-Pitaevskii regime. And this is what I meant that when I said that the Gross-Pitaevskii regime also can provide some hints going to the thermodynamic limit. But the problem is to us that controlling the Jastrow function for such a high value of kappa, so on such boxes which are so much larger than the one corresponding to Gross-Pitaevskii scale, is too complicated to us at the moment. And this is the obstruction for us to extending our result to the thermodynamic limit. We still believe that the trial state in the form that I showed you for the Gross-Pitaevskii case is the correct one, is the one encoding the correct energy, but we are not able to deal with the computation, in particular to the subtle cancellation occurring from denominator and the numerator. And just let me here stress that this localization technique has been widely used in the mathematical community so far. So again, the fact that to compute thermodynamic function, you don't need to show Bose-Einstein condensation on the whole box, but just you need local condensation. But also, remarkably, there is also a novel approach where, in fact, the ground state energy or the thermodynamic function are just studied directly on the thermodynamic limit, and to deal with the fact that the system has a size which is so huge, cutoff function are introduced directly in the Bogoliubov transformation, let's say in the unitary transformation that describes correlation, very much in the spirit of renormalization group approach. So I also wanted to stress. I'm at the conclusions. I hope that I have given you a small hint of the fact that in this past year, the mathematical physics community has gained an enhanced comprehension of trial states for the dilute Bose gas in several physical relevant regime. And I only told the very small portion of the full story, because there is many people involved and a lot of interesting results that they have not had the time to talk about in this talk. A second order upper bound for the hardcore bosons in the thermodynamic limit is still open, and the main difficulty being that the Bogoliubov-like trial state that are usually used to capture the second order leading order terms or sub-leading term do not belong to the hardcore domain. And on the other hand, perturbation of Jastrow-like function that would stay in the core domain are difficult to handle, where we are on boxes which are much larger than the Gross-Pitaevskii box. Also, I only told the story for 3 dimensions, but the same story can be now start to be also be possible to tell something also in 2 dimensions. The leading order has been known since the pairing work of Lieb, Ingvason, Seiringer, and again because basically with this so these Jastrow-like trial functions are very powerful. Basically, once you know how to deal them, then they are valid. They also encode the difference in dimension in them, in a sense. So if you want to capture the leading order term, these are really powerful tools. But if you want to go to the second order, then things become more subtle. So in fact, in a paper with Christina and Benjamin that hopefully will appear soon, we show that to get an upper bound, where we can get both lower and upper bound for 2D bosons, is also the spectrum, because we are dealing with the Gross-Pitaevskii scaling limit, not the thermodynamic one. But here for the upper bound, you immediately see that you need additional correlation with respect to the three-dimensional case. So when you want to go one order further, you need, so the dimension of the system plays an important role. In fact, we know that condensation is crucial in 2 dimensions, so something different also happened, even though we are still in 0 temperature for this paper here. Then another story would be about positive temperature in dilute Bose guys. I only had like the space for quoting a few papers, but of course this would be a very interesting discussion. Also, at the moment, we are in the point where we know the leading order result, but of course, it's much more complicated with positive temperature, with entropy coming in and so on. And then another, of course, interesting question of what happens beyond the dilute regime. Can we say something? An alternative approach to the study of the diluted regime, which has not yet proven to be rigorous, but which is possibly also extending to non-dilute regimes, so to high-density regime, was introduced by Lieb in 1973 and has been recently revived in these papers. And also here, I think I can quote the talk that Jan Jausling gave to Jan. And so to be fair, I also should mention the talk that Ankan Nam gave for the trapped Bose gas. So I would just conclude saying, if you're curious, if you want to know a bit more about this story, I would recommend to hear like the talk by Soren Fournet, Jan Jaslin, and Ankan Nam that are really complementing a bit this story. And thanks a lot for the attention.
Thank you very much, Serena, for this very nice and very clear talk. Is there any question from the audience? So maybe I can start. So what is the status for the excitation spectrum in the Gross-Pitaevskii regime with hard spheres? I guess this is there are no results about it.
You're right. You're perfectly right. So we believe that with our method, so the upper bound should be also valid. So sorry, maybe I take so the impression is that also the spectrum as an upper bound is close. It's easy to get, or we should be able to get, namely, just because you should just prove that. So okay, let me tell better. For this phi, so let's say for the function which is perturbating the Jastrow, we know basically everything. So in particular, we know the low energy state corresponding to the effective function that allows us to define this guy here. So the only thing that you need then to show is that the wave function, the end particle, the wave function that you will just take in the excitation states of that guy. So I mean, that guy I refer to the effective Hamiltonian for which this guy is defined. Time, the Jastrow are still making, so are the good excitation spectrum for the hardcore problem, right? So you should just show that they are close to the excited vector for the full problem, let's say. So, okay, we missed that part. We didn't think to that. Maybe it's also fair that I add that as for the lower bound, of course, our result, so sorry, that the matching lower bound for the Gross-Pitaevskii case clearly follows from the paper by Fournet, Young-Philip, Solovey, and the thermodynamic limit. As I told you, the thermodynamic limit is just on a larger scale, so it includes like the Gross-Pitaevskii result. Still, we hope that with the extension of this method that I presented, we can rather also explore the spectrum for the hardcore case in the Gross-Pitaevskii case. Which I'm not sure is encoded in Jan-Philip Pessoa result, but this is just for the sake of my ignorance, not because I understand. So if someone knows, maybe he can answer. But for sure, our method, if we would be able also to get lower bound, would allow very naturally also for getting the spectrum for the Gross-Pitaevskii case.
Thank you. Other questions?
Yes, can I ask a question?
Yes, please, Al.
Okay, so you cleverly avoided talking about Bose-Einstein condensation, but I'd like to ask about it. So you said you can show the existence of BEC in the Gross-Pitaevskii regime. So what does it mean? Do you have a precise control of the ground state and low energy excitations? Or
yes, precisely. So this means that you really can prove something. Let's see if I. So, but you know, it's not. So of course, it's a nice result that there exists a regime where you can show some Bose-Einstein condensation to occur. But so the limit, you're right. Maybe I should specify what I mean here for Bose-Einstein condensation. I mean that one particle reduced density matrix associated to any low energy state. And here low energy state, I mean states where energy is just close to 4 pi AM by some constant. Well, you can also allow here some kappa depending on n. It's sufficient that is just smaller. So take any low energy state which is sufficiently close to the ground state energy, and then bound.
It's the low energy. Is it the energy eigenstate?
Yes, exactly. It's not the ground state energy. It's just the Let's say take any state whose energy is close to the ground. Any low energy state. So any state whose energy is close to ground state. Build the one particle reduced density matrix associated to that. Then in trace norm, this will converge to the projection onto phi, the condensate wave function that here on the box is just the one particle wave function. But okay, you can do it even. See, this Bose-Einstein condensation in Gross-Pitaevskii case, remarkably, you can just show it in general case where your bosons are trapped by a potential, and there this means that really you have condensation in the minimizer of the Gross-Pitaevskii energy function for the ground state. But which is the limit here? Sorry, this is important thing. The limit here, when you get this convergence of the one particle reduced density matrix towards like a projection on the one particle state, the condensate state, is a limit n to infinity. So you are sending the number of particles to infinity, but the volume is kept fixed to 1. So basically, this corresponds to show condensation on a local, let's say. It does not correspond to like the not decay of correlation on the thermodynamic limit, right? So it just corresponds that on a local scale, raw correlations stay constant. So still it's remarkable, this information, because this local condensation property allows you to get plenty of information on this local energy, let's say on the information on local thermodynamic function, and even to provide, to show that the spectrum locally on these small scales behaves as the one you would expect if you were able to prove Bose-Einstein condensation in the sense we mean, like a linear spectrum. But again, there is a trick, right? Because we are in this finite box, so we have a gap. Yes. So we are basically only doing the solving the ultraviolet problem, and from that scattering length arises from that ultraviolet renormalization. Let's say that here is just like encoded in this unary operator, but we are not dealing with the infrared problem. So I would say that we are here at the same stage where maybe in the work by Horst, Balaban, Knorrer, they are, namely that we cannot go in the true infrared region. So for the Gross-Pitaevskii case, there is no infrared region in a sense, right? There is just a P, the first P is 2 pi, the first P different from 0. So we only like study the ultraviolet problem here. I think now the best available result that we have is the one by Balaban, Trubowitz, Horst, Knorrer, And they can arrive at the moment, they can perform a renormalization group argument, also controlling large field, and arrive at the moment where the onset of the two wells appears. But yeah, so sorry, Hal, I hope this makes clear why in this case we can prove Bose-Einstein.
Yeah, thank you. Yeah, it was very clear. Thank you very much.
Thank you, Serena. Other comments?
May I have a question?
Sure.
The naive view says that upper bounds are easier than lower bounds.
You're right.
Here, this seems not to be the case. Am I correct?
Yes, you are correct. So even though I'm not such an expert in the work by Jan Philipp and Søren, so they may also claim that also there the lower bound was, very hard to get for the hardcore case. But what I can tell you that here to us seems like that, right? This requirement to be in the correct domain, this makes the upper bound so difficult. For the lower bound, you can just approximate your potential with increasing potentials. Let's say a sequence of potential that are going, whose L1 norm is growing. And then if you are able to show that your bounds are uniform in this L1 norm, then you can conclude. But for the upper bound, you really need to stay in the correct domain. And this is the issue. So you need to put n-square correlation. So the point, I think, it's all that, right? So this Bogoliubov-like trial state are so clever that they allow to put you only a few correlations, which are in fact the ones that are enough to capture the energy. But you are not putting all the possible correlation among the particles. While when you want to use, like, to encode this hardcore condition, you should really take into account for n-square correlation among the particles, and that makes the computation so complicated. And also another comment, completely unrelated, but just because you mentioned that the upper bounds sometimes seem more complicated, we were also very surprised, but this is also what happens for two-dimensional in Gross-Pitaevskii regime. So for the lower bound, due to the fact that the potential is positive and you can throw out, basically the strategy is the same of the three-dimensional case up to, so here I mean to get the second order upper bound, two-dimensional boson Gross-Pitaevskii regime. So the one where the scattering length goes as exponentially small in m. So by the way, you just try to do the same trick that you do in 3 dimensions, just with adjustment due to the dimension, of course. But for the lower bound, it goes smoothly. For the upper bound, no. For the upper bound, you need additional correlation, which are quartic. And this quartic correlation also seems to be connected with the fact that in 2 dimensions, quartic term, not only cubic term, but also quartic term are relevant in the sense of renormalization group approach. But by the way, this is another example where the upper bound costed us much more energy than the lower bound. You agree? I don't say it's, yeah, sure.
Another question, you mentioned cubic transformation, which sometimes is needed and sometimes not.
When you mean?
When and about this cubic, I mean, in the slide, you in this cubic transformation, you mixed B operators and A operators.
Yes.
Can't you use only B operators, which are, I mean, just for uniformity?
Yeah. Sorry, I should have lined like that then. Sorry, I think this was only my error. Thanks, Jan. You recognize the error in the slide because this was exactly not. They are all. So I took a slide where was a proof of condensation. For the proof of condensation, the operator that you need is one like that without the A star. So it's A star A. So this makes perfectly sense in the space. But when you want to do Bogoliubov theory, then yeah, thank you.
Okay. This.
But so no, thanks to you. Of course, this is just because you want to stay in the canonical ensemble, right? Because if you are rather interested in the grand canonical, if you are rather interested in the thermodynamic limit, I mean, the upper bound for the Lee-Huang-Yang formula and the Gross-Pitaevskii in the thermodynamic limit that I had no time to discuss, which is like the trial step that we exhibit with Julia and Benjamin. There it's only A star that you need. Then you do everything in the Fock space, in the Crank canonical, and then you have a equivalence of ensemble. But your question was very, very interesting. It was when you need and when you don't need this cubic conjugation. They are really needed. So, and the answer is also, maybe I'll write here, very easy. So basically you have this potential N3 beta minus 1 Pm beta X. Okay, and again, we were saying that in a line of beta, so there is beta equals 0, which is the mean field regime. Then there is beta equal 1, which is the Gross-Pitaevskii regime. And then there are two other interesting thresholds, which are 1/3 and 1/2. So 1/3, so for beta less than 1/3, basically the range of the interaction is much larger. So for beta less than 1/3, range of interaction is much larger than the interparticle density. So this regime is still a sort of mean phi-like regime. So you don't need, in a sense, to add correlation. Then there is this other threshold here. This defines a region here where basically, if you're interested to the ground state energy, you can approximate A as the first and the second Born expansion of the scattering length. So in this region, beta less than 1/2, Bogoliubov theory is correct. Really correct. Namely, you can throw out the cubic and quartic term, prove rigorously that they are small, and then you only need to put as a trial state the one that diagonalizes the Bogoliubov Hamiltonian, sorry, the quadratic part, and then the vacuum, and then of course I should also put the condensate here. Okay, so here mean field, so this was explicitly written by Robert, right? So there is a sorry, you also worked on that. So here, but you can really extend up to 1/2. Then this is the region where things start to be different. So as beta is increasing here, in order to get the precision you need for the ground state energy, you should add more and more terms in this expansion, up to the point where for the Gross-Pitaevskii regime, all terms in the expansion are needed. So, and when all the terms in the expansion are needed, so this means that really, so for the Gross-Pitaevskii regime, basically there is no Born series, right? So the Born series for the scattering expansion is a series in range out of scattering length, contrary. A over scattering length. So in general, this would be n-1 plus beta. So as long as beta, this parameter beta is less than 1, there is a series. It's just that you need to collect more and more terms in this expansion. But as long as you have in the GP case, and this A over R is order 1, no point, in order to reconstruct things, you need the cubic. So basically, you need the cubic transformation, I would say, when this Born series does not, you cannot write it.
Both for the lower bound and the upper bound?
Sorry?
Both for the lower bound.
Those, so this picture that I told you so far works both for the lower and upper bounds.
Okay.
But just because we are in this mean field, in this scaling limit, right? So in the scaling limit, basically the ideas for the lower bound and the upper bound are basically the same. So the upper bound, you would be always able to make it shorter. But in a sense, all our papers use the same strategy, which is just conjugating with unitary operators. So you have all equalities up to errors. So basically in this scaling limit, you have all equalities up to errors. But of course, then the same picture in regimes that I'm not sure I'm able to write you by hands, but the same picture also holds in the thermodynamic limit. In fact, the work by Giuliani Feiringer, so okay, sorry, this is a comment for the lower bound. So for the upper bound, basically the work by Erdo, Schlein, Yao, so where they only use like the quadratic correlation, so no cubic. In fact, they could only get the correct result for lambda small, potential small. Potential small means that you have a Born series, because you have this small lambda allowing you to get the Born series. So no cubic if lambda small. But you need the cubic. This was Yao Yin amazing understanding. I think they were the first adding these tripods of excitation, allowing at least to express a trial state, putting them into place. And they say that you need cubic to get Lee-Huang-Yang. And for the lower bound, I think the first paper by Giuliani-Zeilinger, 2008, something like that, they were very, I find it such a nice paper. So the result, of course, is just limited in a regime of parameter, which is not precisely the one that is in high density, weak coupling high density regime. But in fact, what they notice is that there exists a regime corresponding to here, in a sense. So in a regime where really you can make the prediction of Bogoliubov theory valid, basically that you can throw out all the terms. So just I think the nice part of this paper is just they figure out a regime where they could throw out, so they could show that Bogoliubov theory was correct. And then of course this has been later extended. So here they were, for the lower bound, really for this thermodynamic limit, then all these localization techniques are really crucial, right? So here they were really using a basic localization, which were making them lose a lot. But then in a paper by Brennecke, Solvay, it was introduced this double, so it's more sophisticated localization. And this more sophisticated localization allows you to really go beyond, let's say, this very first result. And this is the localization that also allows Jan Philipp and Soren to get the amazing lower bound. So sorry. So what I meant here is also in the thermodynamic limit, you can recognize a picture like that. It's just that you should put into place the correct row and the correct parameter that enters there. So again, from a physical point of view, it's really clear when you should expect cubic correlation to come into play. And if you're asking me if I can recognize also the quantum correlation for the 2D, why they should come, I'm not sure I'm so confident again. So I was just expecting them because of the work on the renormalization group, perturbative work we did with Alessandro Giuliani on two-dimensional noise gas. So I was expecting quartic correlation or quartic renormalization to be needed at a certain point, but now I cannot tell you why in this picture in the other way, so I should think on it. But anyway, for the cubic correlation, it's really, so maybe I was not good enough in explaining the idea, but it's really the physics and also, let's say, the previous work that really guides you in understanding what is missing in a sense. Sorry, Jan, I don't know if I answered.
Well, thank you. The answer was very interesting.
Are there other questions from the audience? Okay, so it doesn't seem to be the case. So let's thank again Serena for the nice talk and very interesting discussion. And we can now